Okay, so I decided to include this example because I believe Nichapon asked something about when we have the settlement and what would we do with the moment distribution. And I don't know why I did not include this in the beginning because it has the relationship with the moment distribution for the size wave frame as well. So anyway, so you guys gonna have to copy this, okay? Or actually you can take a photo and then, you know, things like that. Okay, that's 6 meters. I use 6 blocks. And we have the point load at the 4 meters location. That's a 60 kilonewton. Okay, that's a 60 kilonewton. And this is 4 meters. And this is 2 meters. Okay, and we have the support here. That's 2, okay? And then we have 8 meters. And then we have another 8 meters. Oops, sorry. It's fixed. And we have the uniform load of 20 kilonewton per meter. And this span is I, the moment of inertia is I, this is 2I, and this is I, okay? And we have the case of settlement. Okay, so this is, let's say this is our datum line. This one comes down 30 millimeters. And this one comes down 50 millimeters. Okay, so you would know that your beam is coming down like this and like that. All right, so again, what you should notice is that you will have the moment due to settlement. Okay, and notice that this guy is rotating clockwise with that member. I don't have a name for it yet, so let's call this one A, B, C, and D, okay? So AB rotates clockwise, and you know, we always calculate the resisting moment. You should know by now that the fixed end moment is the resisting moment or the internal moment, and the direction is always, you know, opposite of the load. So if the member AB wants to come down clockwise, you would know that your fixed end moment would be counterclockwise. Okay? So your fixed end moment would be like this, and you would expect it to be negative. And member BC would, you know, rotate clockwise as well, and therefore the fixed end moment would be counterclockwise or negative. In the meantime, member CD is rotating counterclockwise. Therefore, your moment that will resist this would be clockwise. Okay. Now, before I begin anything, you see, I don't know if you're going to be happy or unhappy to see that in this case, you cannot modify anything, right? There's no simple end support and it is not symmetry. So we just gonna have to hit it head on, okay? Now, before I do anything about that, let me try to change the page because I want to preserve the space down here for moment distribution. Another reason that I want to show you another example is that for those of you who haven't started your active session on moment distribution, or those of you who have and still confused about something, you get to see more examples. Okay, and I'm gonna do it to show you again. So you know your understanding should be better after you see more examples. Okay, and let me flip the page back to this, and I'm gonna use the area here to show you that. Yeah, if you have the different settlement, say this is your beam, and say if it wants to come down like that, it's kind of ugly. Let me do it again. Okay. Oh, geez, wrong one. So let's say your moment has a settlement and it wants to come down like this. So your member is rotating clockwise. You're gonna have the counterclockwise moment. All right, and we have the formula here that somewhere in the sheet as well, that Mij is equal to Mji, and it is equal to minus 6ei delta over L square. Okay, and to be able to calculate the friction moment due to settlement, now you need to have the EI value. Okay, and for this problem, EI is given as 8,000 kilonewton meter square. Okay, so we can now use this formula to calculate the moment, and I don't have the calculation for the friction moment, but I can do it now. And in doing this, you need to be careful because EI is Newton per square meter. Okay, so if you want to do this, this moment should be equal to minus 6 if EI is 8,000. Okay, and for the first member, it is 30 millimeters. Okay, so it is 30 divided by 1,000 to make it meter, right? And then L square, that would be 6 square. Okay, that's for AB. And for member BC, that's going to be the same name. Okay, I mean the same numbers, 6 and then 8,000. But the displacement is now, because you have 30 millimeters and 50 millimeters, so this one should be 20, right? You see, that's delta. Okay, and divided by the total length is 8 meters. And then MCD, this guy is the member is rotating counterclockwise, so you have the clockwise moment, so it's plus 8,000, and the settlement is 50 millimeters. Okay, and the length of the member is 8. Okay, and you do have the, say let's put a prime on it so that you know this is moment due to settlement, and I have FEM AB, that is also equal to 60 4 square 2 divided by 6 square, right? And this is the minus 1. And then FEMBA, it's this is a plus 1, 64 2 square over 6 square. And then I also have FEMBC, right? That is minus what do we have here? 20. L is 8 square over 12. All right, so that's everything. Okay, we got it covered, and there's no need for me to show anything about the relative stiffness. This guy should be straightforward. So I'm just going to put things into the table, okay? Not easy to try to make it straight, but I think I may have got it. Okay. All right. And this guy is 0 because it's a fixed support. There is no lock and release process required because you already have the lock joint. This is I over 6 and 2I over 8, that's I over 4. So basically I over 6, I over 4, so that is 2/5. This is 3/5. And this is 2/3 and 1/3. Because I is twice bigger, they have the same length, right? But now we can start. Now this time, yeah, you must believe in superposition, right? So I have the fixed moment. This is equal to 20 minus 26.7. This is 53.3. I think I may have made a mistake here. Yeah, right. The FEMBA should be, yeah, it's not easy to remember the formula, right? Because the load is there. This is 2 square. This is 4 square, right? Okay, my apologies. This yeah, FEMBA should be greater than AB because the 60 kilonewton is closer to B than A. Okay, and here we have minus 107. 107. This is fixed moment, and then we have moment due to the settlement. This is minus 40. Minus 40. Just look at the sign, okay? The moment due to resist the settlement should always have the same sign convention on both ends of your member. Okay, and we have here minus 30. Minus 30 because you know these two pairs, they are negative because your members rotate clockwise, so you have counterclockwise moment. But for the last one, it is positive because your member rotates counterclockwise. Okay, and then that's it. That's just about the only thing that I can actually stop here, but you know, because I said that I would want to, you know, demonstrate how things work out for you. So this is the fixed moment. I shouldn't draw the solid line because we haven't balanced anything yet, right? Okay, it's just the dotted line to show you, okay, this is the fixed moment. So you need to balance this. Okay, now we're gonna balance it by, let's say we use the red, okay? And I'm gonna balance this first, and we have so many here, so you guys better be careful, okay? This is in total, we have minus 177 and plus 53, so it's like minus 123 kilonewton meter of moment we need to balance, and we need plus 123 of that, and 2/5 is going to come from the left, so this is 49.36. Very confusing because in my note I use blue, but I don't know why I use red here, but you know, doesn't matter. So here is 74, say 0.1. Okay, again, notice that after the first cycle, this sigma moment, after you balance everything, this better be 0. Okay, and we move on to the second support. This is about 114, yes, so you need minus 114, and 2/3 is going to come from member BC, so this is minus 76.5. Here is minus 37.7. Okay, and again, after you balance your moment, this better be 0. So now this time we can truly say this is the end of our first cycle. And you now may begin your carryover. If the moment exists on one end, on the opposite end, it should have the corresponding value about a half of that. Okay, so this is 24.68. This guy comes over here, minus 38.25, around that. Here, it's 37. Look like 3. Let me do it again. 37.0, okay. And then here we have minus 18. That's sorry for my eyesight. This is not the 37.5. It is 37.7. Okay. Oh, sorry. I actually 5 is correct. 7 is it's the red one. Ooh. Okay, so we carry from the red one. So now you have your second cycle that you need to balance, and the same procedure will begin again. This you don't have to balance because it's already at the fixed support. You have to balance minus 38.25, and we have the 15.3 here, and 20, let's say 23.0. Okay, and here you need to balance 37, and you need to have minus 24.8 and minus 12.2. Okay, and that again is the end of your second cycle. And please do always check every cycle, because if each cycle is correct, in the end your answer should be correct, and you don't have to have a headache and a heartache. Say if in the end it's not 0, oh, one of my cycles is wrong, and if the wrong cycle is at the very top, you got to do it again. And when you do it again, things become untidy, right? So check the cycle here and the cycle here. If they are 0, you can move on. Carry this over. It's about 7.65. Carry this over. So that's minus 12.4. Move this, and it is 11.5. Move this here. It's minus 6.1. Okay, and balance it again. That one. Maybe I can turn this into a red one. Balance this again, and we have 4.96 here, 7.44 here, minus 7.69 here, and minus 3.79 here. And that is, after the balance, it's the end of your cycle. Okay, and again, we keep doing this until the number becomes small enough. 2.48, and then here is minus 3.85. Here is a half of that is 3.72, and then a half of that goes to that support, minus 1.89. And oops, here we go again. Okay, so balance it one more time, and let's say, okay, I have 1.54 here, I have 2.31 here, I have minus 2.49 here, and I have minus 1.23 here. So again, that's the end of another cycle. Okay, and well, if you're crazy enough, let's do it one more time to end it properly. 0.77. If you do it like enough times, you know, you should get the same answer as the moment distribution, because if you notice, this is the mathematical approach that is used to help solve the equations in slope deflection. It is completely based on slope deflection. Okay, so we have a minus 1.25 and 1.16 here, and the number is small enough, you know. But you know, let's say the common mistakes that some of you can make is that, okay, you carry it over, the number is already small, so I'm just going to end it here. You cannot end by carrying the moment over. You must end by balancing them. Okay, otherwise this cycle, the last cycle, will not become zero. So you need to balance it one more time before you can say, okay, I'm done. So here it's another balance. Minus 0.78 and minus 0.38. So after you balance it, and that's it. And you don't have to do anything with the fixed support because there's nothing to balance with. But if you could, you know, just to say, I get the most accurate number, you may want to try to send this over one more time. But you don't need to send something in between over, because again, if you do that, you need to balance it. But you can always send more moment to the fixing if you want. Okay, so in the end, but I'm not going to do that. In the end, let's say we have minus 31.1 here. We have, actually it's 84.96 and minus 84.96 U bet. If you check every cycle, in the end, it must be, you know, zero as well. 17.82 and minus 17.82. Okay, and this is 10. Let's say 10. Okay, but that's it. Okay, any question? Okay, so if you know the settlement, you can use this formula for the fixed moment to calculate the number, and then you can begin with that. But you now know, if you are facing with the side sway frame, you don't know how much your frame is going to sway. So in that case, you cannot calculate your fixed moment. We have to come up with other means to solve that. Okay, so all right. This is it for this example. And before that, we have another thing to address. And that is how you can take advantage of the symmetry. Okay, so let's us take a look at the PowerPoint, the handout of the class. Where is it? Oh, here it is. Okay, so I have this, symmetry and anti-symmetry conditions. Okay, for this, we actually have 4 cases, 4 types of symmetry. Oh. 4 types of symmetry and anti-symmetry conditions. So we have, let's say, the odd number of spans and the even number of spans. Okay, odd means like 3, 5, 7, 9, 11. Even would be 2, 4, 6, 8, 10. Okay, so for the odd number of spans, oh, that's my handwriting. Let's say for the odd number, let's do it again. For the odd number of spans, if it's symmetry or anti-symmetry, your center line is in the middle of the member. See? But for the even number, it's right at the mid support. So there are the difference. Okay? And what would give you the symmetry and anti-symmetry conditions? Can anyone answer? I guess not. So symmetry would be, you would have both symmetric structure and symmetric loading condition. You would get symmetry. But for anti-symmetry, you get symmetric structure, but anti-symmetric loading condition. For example, you would get symmetric if I put the load like this, right? But you would get anti-symmetric instead if this load is like that. Okay? All right. So the fact that the center line, the line of symmetry, is right at the middle of the mid member or right at the middle support, it gives a different behavior to the structure. So when we have a symmetric condition at the center of the member, like this. Let's say I will put it back to symmetry first. And I don't know, if you have the picture like this, so let me try to put more load, okay? So it just resembles that. You're gonna have your line of the deflected shape like this, perhaps, okay? Then like that, okay? When you have this, let's say now we know that in order to have symmetry in this first case, the zeta B here, and then zeta C, the zeta C must be equal to minus zeta B, right? So that you have that. So again, we start off with our slope deflection equation, and you plug in zeta B equal to minus zeta A. So the stiffness becomes 2EI over L. And our common stiffness is 4EI over L. So this is 2. So that means the K modifier is 50% of the original. So if you have this case, your modification becomes 0.5. All right. The next one. Okay. Anti-symmetric at the center of the member. So it is this one. Okay, so let me draw it again here. One moment, please. Like this, you know, so this one perhaps will go down, but this one will go up. And this is your line of symmetry. So it means that it should go like this. So you see, can you imagine, you know, when you're trying to load the beam so that it has a double curvature like that. So, you know, you should imagine that this is pretty stiff. And again, for you to have this, it means that this rotation, they actually go in the same direction. So you guys, you know, if you go back to slope deflection and see if you try to utilize the symmetry and you use the wrong value. Let's say you say theta c is equal to theta b. This is what you say, and it is completely off the correct behavior if it's not anti-symmetric, you know, because by saying theta c equal to theta b, and you plug in your slope deflection equation, this time you have 2 theta b plus theta b, and then you have 2 up front, so you have 6 EI over L instead of 2. Because as I say, to try to bend your beam like this is extremely difficult. So that makes your beam way stronger compared to the original loading condition. So that means your K modifier becomes 1.5. Okay, and now this even number of span oh, support is so big this time. Anyway, you know by now because you have done it before, right? The rotation here must be 0. Otherwise, you cannot have the symmetric condition. So if theta b is 0, now when you look at this rotation, it becomes just like 2, and then let's call this A, okay? Then this is B. So you have 2 theta A plus theta A plus 0. So this becomes 0. So it's 4 EI over L. So when you have this, whether you choose to modify or not, you already have a very good advantage because the K modifier is equal to K original. So whether you decide to modify it or not, it means that you are ready to take advantage of the situation. Okay, now it's the last one. If it is anti-symmetric, okay, so let me take advantage of this picture. Oh, okay, I can draw another one for you. Let's see if I have enough space for that. Okay, let's hope so. Let's use that as my line of symmetry, okay? And likewise, you know, for this case, we gotta have this kind of loading. And this time, you know, your curve look like that. Oops, no. This goes up, comes down, goes up, like that. You know, the picture is a little bit different, but you know, you get the idea, right? So this time, it's just like the typical slope deflection. You know, if you can recall the modification where if this is theta, this opposite is theta over 2. Okay, you can go back and look at this. Let me try. See, that's simple end support. It's the same thing. So you can utilize this here, and now you realize that, you know, K modify is equal to this, which is similar to the simple end support itself because of the relationship of the rotation. Okay, so right. That means we now have the modification. So don't be afraid to memorize this, because generally I would always give this value in the exam, but I don't think anyone bothers to look at it, and it is right there. So let me, you know, stop the share. No, I mean, not the, right. I need to stop the share, and I will share this screen instead. Okay, this is generally the page that I give at the back end of the exam. You know, the formulas for fixed moment. You don't have to memorize anything. It even includes this. It even includes the formula for your settlement. And right here, oh, okay, can't move that anymore. Right here, you see, I also give this K modifier for everything. Symmetry, symmetry. Generally, I don't give you the anti-symmetry because it's very rare for you to have it. Okay. So, all right. Before we begin to see some examples about symmetry, let's say we should have a break. Okay. So, do you guys have any question you want to be recorded? I guess not. So, okay. Let me stop the record.